Distinguish between types of discontinuity. So the first thing we need to review are the different types of discontinuities. And there are three different types of discontinuities that we have reviewed before in pre-calculus, and those would be the removable, the jump, and the infinite discontinuities. Now just to quickly review, here is the graph of the removable discontinuity. As we can see, there is a hole in the function at x equals a, and that is a requirement for a removable discontinuity. However, as you can see in this particular graph, we do have the function value just removed above it. A removable discontinuity does not have to have that point. It can just be a hole in the graph. A jump discontinuity is where the left side does not meet the right side, and there's this jump in the y values. And then finally, an infinite discontinuity means that there is a vertical asymptote. Alright, so now we're going to be given a bunch of graphs, and we're going to be asked to identify what type of continuity we are seeing in the graph. So for our first example, we want to identify the discontinuity at x equals 1. So first thing I'm going to do is I'm going to come in here, I'm just going to draw that imaginary vertical line at x equals 1, so we know what we are talking about. Not what, excuse me, where we are talking about. And as we can see, there is a jump in y values between these two particular functions. So that means that this would be a jump discontinuity. Woo! One example done. Now we're just waiting for the Wi-Fi to catch up with my writing. Come on, box. Quick, quick. There we go. Gotcha. Alright, so next time the next example we're given is a new graph, and this time we want to identify the discontinuity at x equals -1, so along this line right here. Now this is an interesting graph because the limit from the left and the limit from the right come together and they form kind of this peak, or this cusp, as we will later refer to it in this course, but right now we can see there is a hole at that part of the graph. I mean, it happens to be that the hole or the point is down here, but since they are not in the same spot, that means that this particular graph has a removable discontinuity. And Wi-Fi is a little bit slow today, folks. Sorry about that. Come on, answer box. Go, 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 go. Go, go, gadget, answer box. Awesome. Alright, in our last example from graphs, we want to identify all the discontinuities in this particular function. So now we're not told what x values to look at, we are just told to look at the graph and identify the discontinuities. So I'm just going to take my quick highlighter tool and I'm going to go through, I'm going to highlight all the x values where it looks like discontinuities are happening. And our first discontinuity appears to be at x equals 0. And we have one at x equals 2, x equals 3, and x equals 4. So we have 4 discontinuities here. So we'll start out with x equals 1. Ooh, 1. Did I say that? I lied. I'm going to start off at x equals 0. Alright, x equals 0. The y value coming from the left does not equal the y value coming from the right, which means that at x equals 0, there is a jump. Alright, next up we'll take a look at x equals 2. And x equals 2, the limit from the left does equal the limit from the right. It just so happens that the f of a value is not defined, which means that this is a removable discontinuity. Then at x equals 3, we appear to have a jump discontinuity because the limit from the left does not equal the limit from the right. And then finally, let me just get rid of that circle there so we can see what happens at x equals 4. So at x equals 4, we can see that both sides of this particular function goes to infinity. So this would be an infinite discontinuity also because of the vertical asymptote. Next up, we're going to be looking at distinguishing between types of discontinuities from equations. So since we're dealing with equations now, those three conditions for continuity are going to come back into play, with f of a needing to be defined. The limit, as x approaches a of f of x, has to exist, and the limit has to equal the function. So again, if f of a is defined, that removes the infinite or part of the removable discontinuities. If the limit exists, that removes the jump aspect of the discontinuity, and if the limit equals the function, that removes the removable discontinuity piece. Alright, so for our first example here, we want to determine whether f of x is continuous at x equals 2, and if it's not continuous, identify the discontinuity. And we're given a piecewise function here. We're given f of x is equal to x plus 1 for all the x values that are less than 2, and 2x minus 1 when all the x values are greater than 2. Alright, so we can see here that our piecewise function is based around the point x equals 2. And as the problem tells us, that is our a value. So again, we're trying to determine whether or not the function is continuous at this particular point. So first off, to do that, I'm going to kind of draw a number line and determine where on the number line each one of these pieces is going to fit. So quickly drawing a number line in here, boop, 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 boop. I'm going to put the a value in the middle, which is 2. Now I can see that our function is going to be x plus 1 for all the values less than 2. So we're not going to include 2, it's just all the values less than 2. So I'm going to shade in all the values less than 2. And again, for this part of the number line, I would use the function x plus 1 when I'm using any of these x values. Then for our second piece, the function is going to be 2x minus 1 when x is greater than or equal to 2. So that means this expression will be used when x equals 2, and then for all of our x values that are greater than 2. Alright, so now that we have this number line, we know which part of the graph is going to be which expression of the piecewise function. So now we can dive into the 3 conditions of continuity. So our first condition of continuity is that f of a is defined. So we need to check this condition. So again, we're told in the problem that our a value is 2. We also know a would be 2 because that's where our 2 piecewise functions will hopefully be connected. So that means we're going to be looking for f of 2. Now we just need to figure out which piece of this function we're going to be substituting 2 into. So we have to determine, well, which of these domains of the piecewise functions includes 2. And from the graph, we can see that 2 is included in the blue piece, or the 2x minus 1 piece. And we also know that from the equal sign of the inequality. So we're going to take that piece of our piecewise function, and we're going to plug 2 in for x. So let's see, that's going to give us 4 minus 3. Oh, excuse me, it's going to give us 4 minus 1, which will be 3. And there we go. This condition is satisfied. F of a is defined at 2. Next condition, does the limit as x approaches a of f of x exist? And we know that in order to check that, we need to check the left-sided limit and the right-sided limit. So here we go. We know we're going to have to look at the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. Going back up to our number line, we can see that as we approach 2 from the left, we are going to be using the red expression, or x plus 1. And when we are approaching 2 from the right, we can see that we are in blue territory here, which means we're going to be using the expression 2x minus 1 to evaluate that limit. Alright, then from here, x plus 1 and 2x minus 1 are both polynomials, so we can use direct substitution. So we're going to get 2 plus 1, which will be 3. And then the limit from the right is going to be 2 times 2 minus 1, which will also be 3. From here, we can see the limit from the left does equal the limit from the right. Those both meet at the same height, so therefore we can say the two-sided limit, which is the limit as x approaches 2 of f of x, does indeed exist, and it exists at 3. Alright, so 2 conditions down, 1 left, and this is the easiest one. This is also often one that students sometimes forget to write down because it's so obvious. However, it is super important to write it down because in math we have to know what you're talking about, and you have to demonstrate that all three of these conditions are satisfied. By just doing it in your head, you're not demonstrating anything. So please make sure to write down all of these conditions and don't stop when you think it's obvious. Alright, so again, the third condition is the limit equal to the function, or is the intended height equal to the actual height? Let's see, from condition 2 we can see that the limit is going to be 3. And from condition 1 we can see the function value is going to be 3. And 3 does in fact equal 3, so therefore the third condition is satisfied, which means that our function f of x is continuous at x equals 2. And there you go. We have just used the three conditions of continuity to prove that this piecewise function is continuous at x equals 2 algebraically. Alright, so next up we want to determine whether f of x is continuous at x equals 1. If not continuous, identify the discontinuity. And for this particular function, we can see we're given a rational function, and we are not given a piecewise function. So we're still going to go about this the same, we just don't necessarily need to draw the number line to figure out where the pieces go, because there is only one piece. So we'll start out with our first condition, does the function exist? So we're looking for, is f of a defined, And we can see here that the problem tells us a is going to be 1, so we're trying to figure out whether the function is defined at f of 1. So we will plug in the 1 into our function, giving us 3 times 1 squared plus 2 times 1 plus 1, all over 1 minus 1. And then we can come in and we can simplify this. 1 squared is 1, 1 times 3 is 3. Plus 2 times 1 is 2, plus 1 over 0, which is going to give us, I said 0, but then I wrote 6. 1 minus 1 is 0. The numerator will then be 6 over 0, and therefore this is undefined. Alright, so that means that condition 1 fails. So we know the function is not continuous at x equals 1. So then we need to move on to the second part of the direction. So if not continuous, identify the discontinuity. Well, if condition 1 fails, we know that there's either going to be a removable discontinuity, aka a hole, or there's going to be an infinite discontinuity, aka vertical asymptote. So now we just need to figure out which one of those two discontinuities it is. And we can figure that out by moving on to our remaining two conditions of continuity. So moving on to the second condition, we will investigate whether the limit as x approaches a of f of x exists. Because if the limit exists, that means the limit from the left and the limit from the right meet at the same spot, which means that there won't be a vertical asymptote, and so that eliminates that option, leaving us with a removable discontinuity. So, let's dive in. So, if we look at the limit as x approaches 1 of 3x squared plus 2x plus 1 over x minus 1, if we were to do direct substitution, we would end up with 6 over 0. And this tells us that's a number over 0 form, which should be setting off alarm bells in our head saying table, table, table. Alright, so that means we need to look at the limit from the left and the limit from the right, but we are going to have to set up a table. So limit as x approaches 1 from the left, actually let's do that in a different color. Lots of purple going on. So limit as x approaches 1 from the left of f of x, we'll have our x and our f of x. And we're going to be approaching 1 from the left, so we'd be using the inputs 0.9, 0.99, and 0.999. Then looking at the limit as x approaches 1 from the right of f of x, we will also have to make our table, but this time we're coming from the right, so we'd use 1.1, 1.01, and 1.001. Alright, then from here I'm going to throw this into my calculator and use the table feature to spit out these values nice and easy. Let's let the calculator do all the heavy lifting. Alright, so let's see, when I plug in 0.9, I'm going to get, wrong color, negative 52.3. When I plug in 0.99, I'm getting negative 592. And 0.999, I get negative 5,992. And remember, we usually want to pick 3 test values to make sure that we recognize a pattern. So as x approaches 1 from the left, we can see that our left-sided limit approaches negative infinity. And then if we do the same thing for the right-hand side, when I plug in 1.1 in my function, I get 68.3, 1.01, 608.03, and 1.001, I get 6,008. So as we approach 1 from the right-hand side, we can see that that height approaches infinity. So from here, we can see that the limit does not exist because the limit from the left goes to negative infinity, the limit from the right goes to positive infinity. So this tells us that we're going to have an infinite discontinuity at x equals 1. So now we've answered the question. So let's see. F of x is not continuous at x equals 1 since there is an infinite discontinuity. Alright, so we have answered the question, we have said that it's not continuous, and then we have also identified the discontinuity here to be infinite. Alright, in our next example we're going to do the same thing. We're going to determine whether or not the function is continuous at a point, specifically x equals 3. And if not continuous, we want to identify the discontinuity. So here we have a 3-piecewise function, negative x squared minus x minus 2 when x is less than or equal to 2, negative 3x minus 2 when x is between 2 and 3 but including 3, and negative 2x minus 2 when x is greater than 3. So, just like before, we want to identify a couple things here. First off, we were told the point for which we need to check continuity, so we know that a is going to be 3. And then we can come and we can plot our pieces on the number line. And we can see that there are 2 spots where these pieces may or may not connect. The first one is 2. The second one is 3. So we would be using the expression negative x squared minus x minus 2 for all the values less than or equal to 2. So I will be including 2 in this piece and shading all the values that are less than it. Then we know we're going to use the expression negative 3x minus 2 when all the x values are in between 2 and 3 but include 3. So I'll include 3 in this shading, and then we can shade that area in, and this will be negative 3x minus 2. And then finally our last piece for all the x values greater than 3, and that piece is going to be negative 2x minus 2. Alright, so now we need to check our 3 conditions of continuity, determine whether or not it's continuous. If it's not, identify the discontinuity. So we'll start off with our first condition. F of a is defined. Now remember, we're told that our a value here is 3. So that means we're going to be looking for f of 3. Now we just need to determine which piece of the function includes x equals 3 in its particular piece. And as we can see, it'll be the middle, or the blue, function, negative 3x minus 2. So we'll substitute in x for that, so negative 3 times 3 minus 2, which is going to give us negative 9 minus 2, or negative 11. So therefore, our first condition is satisfied. F of a does exist. Next up, we need to see if the limit as x approaches a of f of x exists. So that means we're going to be looking at the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. So then we can look at our piecewise function, and we can determine which functions we're going to use for each individual piece. And let's see, as we're approaching 3 from the left, we can see we're going to be using the blue piece, negative 3x minus 2. And when we approach 3 from the right, you can see that we're going to be using negative 2x minus 2. Now you might be asking yourself, okay, that's great and all, but what about our red piece? What about negative x squared minus x minus 2? Great question. That piece is just there. It's part of the function. However, we only care about the point x equals 3. And x equals 3 is nowhere close to that particular expression. So in this case, one could say that expression is given to you just to confuse you, to make you think you forgot something. But we didn't. We just don't care about it. So now we can evaluate our two one-sided limits because they are polynomial, so direct substitution will work. So let's see, this is going to be negative 3 times 3 minus 2, which will give us a value of 11. And then next up, we're going to get negative 2 times 3 minus 2, which is going to be negative 8. So now, unfortunately, the limit from the left does not equal the limit from the right. So therefore, the limit as x approaches a of f of x, I'm sorry, that shouldn't be a. We know what a is. Come on. A is 3. Does not exist. So, our function is not continuous at 3. Now we just need to identify what type of discontinuity it is. Well, if we look back at our first condition, we can see that our function is defined, so therefore it can't be an infinite discontinuity. So the two other options are removable and jump. And as we can see, the limit from the left does not equal the limit from the right. That tells us that there is a jump discontinuity here. So therefore, we can conclude that f of x is not continuous at x equals 3, since there is a jump discontinuity. All right, and there we have it. We have determined whether or not it's continuous, and we have identified the discontinuity. All right, then our last question, same thing. Who would have thought? And we've also already done examples where the function is continuous, where the function is not continuous because of an infinite discontinuity, and where the function is not continuous for a jump. So all that's left is a removable discontinuity. Guess I should have said spoiler alert, but too late now. Alright, so we're going to do the exact same thing that we've been doing before. So we can see here that our a value is going to be 1. And then we can go ahead and we can draw our number line. However, this piecewise function is a little bit different, because while there are 3 pieces, there's only one kind of connector point. So it's not difficult, it's just something to notice. So we're going to plot our a value, and let's see. When x is less than 1, so just less than, we want to include all the numbers less than 1 when we are using the expression 2x plus 1. Now, when x is equal to 1, we're going to use 2. And this function is kind of like a one and done thing, because it's a function for one single x value, which means this is one singular point. And then when x is greater than 1, we're going to use the expression 4 minus x. So that whole point that's included in the piecewise function is just something that we don't typically see, but it's something that we can see because it's just a point, and we're good. Alright, so let's move on. Let's look at our limits, or excuse me, our conditions of continuity. So f of a defined. So we are trying to figure out, is f of 1 defined? So we need to figure out which piece f of 1 exists in, and as we can see, f of 1, or x equals 1 exists in the piece of 2. So that means f of 1 is just going to be 2. Boom, done, defined. Whew, nailed it. Next up, we need to see if the limit as x approaches a of f of x exists. So that means we're going to be looking for the limit as x approaches 1 from the left, and then the limit as x approaches 1 from the right. Now, if we're approaching 1 from the left, we can see that we are going to be using the expression 2x plus 1. And if we are approaching 1 from the right, we're going to use the expression 4 minus x. And these are both polynomials, so we can do direct substitution. So this will be 2 times 1 plus 1, which will be 3. And then 4 minus 1, which will also be 3. And since both of our limits go to the same height, we can say that the two-sided limit, the limit as x approaches 1 of f of x, is equal to 3. All right, 2 down, 1 to go. Finally, the limit as x approaches a of f of x, does that equal f of a, i.e., does the intended height equal the actual height? Does the graph go where we expect it to go? And I forgot to check off condition 2. Condition 2 is good. Woo, check mark. All right, so now using the information from condition 1 and condition 2, we know the limit is equal to 3. And we can see our function height is equal to 2. And those are not equal. So therefore, we can say that our function is not continuous at x equals 1. Now we just need to figure out which discontinuity this is. Well, we said from condition 1, since condition 1 exists, it can't be an infinite discontinuity. Condition 2, the limit exists, which means it can't be a jump discontinuity. So finally, the only discontinuity left is a removable discontinuity, which makes sense because we just picked the point 1, 2 and pulled it down out of the function. So we can now say that f of x is not continuous at x equals 1 since there is a removable discontinuity. And there we have it. Not continuous because removable discontinuity.